everyone, my name is Jackson Crocius. I am a student at Utah Tech University studying geology, and this presentation is a final project for my Geo 3000 level course. So today we're going to talk about deep earth dynamics. Now that sounds really fancy, but really we are going to talk about why the American Southwest, a place that's supposed to be pretty geologically quiet, is actually boiling over from the inside out. So I want you to picture the last time you were in Arizona or southern Utah. Maybe you were hiking the Grand Canyon or driving through those red rock deserts. When you look at the landscape, what's the first thing that comes to mind? A lot of people think ancient or solid, and that's what I would think. It feels like it's been there forever, frozen in stone, right? But here's the thing, that stability is a total illusion. We are standing on crust that is actively breaking apart deep beneath your hiking boots. There is a battle happening between extreme heat and gravity, and right now, gravity is winning. Massive chunks of the continent are becoming unstable, snapping off, and slowly dripping into the Earth's deep interior. It's a process called lithospheric foundering, and it's the reason we have volcanoes in places where they really shouldn't exist. So before we get into the cool volcanic stuff, we have to agree on how the Earth is built. I like to use the peach analogy. We've got the crust where we live. This is like the skin of the peach. It's paper thin compared to the rest of the planet. The mantle is the flesh of the peach. Now, a lot of people think that the mantle is a liquid magma, like the ocean. It's not. It's solid rock, but it's hot rock under high pressure. So over millions of years, it moves like a thick putty, or you can kind of think of it as the same consistency of toothpaste. Then we have the lithosphere. This is the crust plus the cold, hard top layer of the mantle. Together, they form the rigid plates, and these are like the puzzle pieces that make up the surface that we live on. And they float on the asthenosphere. This is your hot, gooey layer underneath. If the lithosphere is a cracker, the asthenosphere is the honey it's floating on. So now we've got that covered, let's talk about plate tectonics. So normally we explain geology using plate tectonics. The lithosphere is cracked into plates, and the action happens at the edges of those plates. So first you've got divergent boundaries. This is where plates rip apart. I mean, you can think of Iceland. You can literally stand with one foot on the North American plate and the other foot on the European plate. When you pull the crust apart, it gets thin, pressure drops, and magma rises. It's basically that simple. So here on the right, we've got an image explaining this process. We've got crustal thinning as the plates are separating and moving in two opposite directions. And you can oftentimes contribute crustal thinning with normal faulting, as seen in the image. And then we've got the pressure dropping and magma rising to fill as the crust is thinning. So let's talk about subduction and convergent boundaries now. So if you look at the image, you've got the oceanic crust doing something we call subducting beneath the thick continental crust. And this occurs at those oceanic to continental boundaries. And this is when the sinking plate gets hot, releases water, and by the sinking plate, we mean the oceanic crust. And it also melts rock, and boom, you get these giant explosive volcanoes like Mount Rainier or Mount St. Helens. These are the big, scary, cone-shaped volcanoes. And that's occurring at these subducting boundaries. That's where you get most of your big, very well-known volcanoes. And it actually forms this area known as the Ring of Fire on the Pacific plate. If you look up an image, I'm sure you can see it. And this is where you get a lot of your earthquakes, your volcanoes. A lot of the cool geologic processes occur at these subducting zones. Our last boundary is transform boundaries. And most people think of the San Andreas Fault, located in California. And these are when plates slide past each other. You get these earthquakes, but no volcanoes because nothing is sinking or stretching enough to really melt the rock. A good way to, well, it's kind of an analogy. A good analogy to think of is if you rub your hands together really fast, side to side, your hands get hot, but you're not creating and you're not destroying anything. And that's kind of how you can think of transform boundaries here. Now you might be thinking, Jackson, why are you telling us all of this? Well, these concepts that I'm covering are really important into understanding the concept I'll be going over later. If you've ever been to Arizona, New Mexico, and Utah, they aren't on any of these boundaries today. We aren't ripping apart like Iceland. We aren't crashing like Washington State. So if we follow the normal rules of plate tectonics, as I've described before, there shouldn't be any volcanoes here. If you've ever driven through Flagstaff, Arizona, or southern Utah, you know that's not really true. They actually have thousands of volcanoes. And to understand them, and understand why, we have to look at physics and how rock melts. And this is when we get into the fun volcanic stuff. So first we've got flux melting. And this is kind of your salt on ice method. If you've ever lived in a cold place, you know that if there's a big winter storm coming and you know your driveway is going to be iced over, you put ice on the roads before the storm rolls in, right? Well, you can think of this as a similar concept. At subduction zones, the oceanic plate drags water downwards. Again, if you think of that image, and I'll actually go back here to help you understand, water is actually flowing with gravity as subduction flows beneath the thick continental crust. And you can actually see that where it says hot fluids. That's where we're talking about there. So back to flux melting here. That water that is being introduced at depth actually acts as salt. It lowers the melting point of the rock until it turns into magma. And this gives us explosive gray rocks like andesite. So let's actually look at the flux-induced melting image on the right. And you can actually see what's occurring here. When you add water, it changes the shape of the melting curve. And this melting curve is basically the point at which rocks begin to melt. So when you introduce that water, it reduces the temperature at which rocks can melt and will start to melt the rocks. And again, remember, this occurs at subduction zones. Next, you've got decompression melting. And this way you can kind of imagine a pressure cooker. Inside the water is super hot, way above boiling, but it stays a liquid because the pressure is clamping it down. If you pop the lid, whoosh, it instantly turns into steam. The mantle is the same way. It's not hot enough to melt, but the weight of the world is clamping its atoms together. If we can somehow lift that weight, if we can reduce the pressure, the rock instantly relaxes and turns into a liquid magma. And this is primarily where you get your basalt, and that's the dark black rock that I'm sure a lot of people have seen. It makes for excellent landscaping and pretty awesome views as well. So our last form of melting is heat transfer. And this is a pretty simple concept. It's basically when you have something hot next to something cold, the hot mantle melts the crust. And that gives us these sticky, silica-rich rocks like granite. So here, you've basically got the rising magma, which is so much hotter than the surrounding continental crust, and that heat will actually transfer into the surrounding crustal rock. And these can often form silica-rich magmas too, like rhyolite. So let's tie it all together. Let's tie everything we're learning into one here. So we discussed the different tectonic boundaries, and we've also discussed the different types of melting here. Now let's see what geologists in the field actually go and do. So when geologists are walking around, they're oftentimes looking at rocks, right? But the rocks actually tell the story. So when we look at basalt, we can think of those divergent boundaries, right? And when we think of those divergent boundaries, we can think of the decompression melting that we discussed before. And so this really helps geologists paint the picture. The rocks help geologists paint the picture of what was occurring in the geologic setting of a certain area. Now let's look at andesite. So another great example of this, again, we said andesite forms at these convergent boundaries. So think subduction, and when you think subduction, think flux melting, right? And that's what's forming this andesite. So when geologists are walking around, they're picking up rocks. Yes, it's fun, it's awesome, but it also paints the picture of what is occurring in a specific area so that we can understand the geologic setting. So more in the geologic setting here are the Quaternary tectonics. And Quaternary just basically is a geologic time. It's relatively recent. And when we talk about the tectonics here, we have to understand why is everything fractured and why is the Southwest being stretched out? So imagine a block of taffy, right? If you pull it from both ends, the middle gets thin and it starts to sag. That's the extension. And when we think extension, again, think the divergent boundaries. Over the last 17 million years, tectonic forces have been pulling the West apart. This thinning crust is the first step. It brings the hot mantle closer to the surface, again, through decompression melting. And this is something that's pretty important to understand here. We get the laramide orogeny, which we're going to talk more in depth later on here, with the interaction between the Pacific plate boundary, and that's a little bit of subduction as well, but we're mainly going to be talking about this idea of basin and range extension. If you've ever seen aerial photos of Nevada, I encourage you to go look at one, because what you'll be looking at are all of these parallel mountain ranges with valleys separating the ranges. Really cool to look at, because that's a perfect example of this idea of basin and range extension. So, now let's talk about the volcanic fields of the Southwest. So this is our crime scene, right? What are we looking at here? These volcanic fields aren't just one big volcano, right? They are clusters of hundreds of small little vents. So let's start with Arizona. The San Francisco volcanic field near Flagstaff, Arizona. This is a huge volcanic field with over 600 volcanoes. And the youngest one is the Sunset Crater, which erupted less than 1,000 years ago. And that's around 1085 AD. And that's not really ancient history. People were living there. They watched their cornfields get burned in the cinders. Then go up to Utah, the Black Rock Desert. We had eruptions there, erupting through ancient Lake Bonneville, creating huge steam explosions. And then New Mexico. The field out here were so fresh they looked like they were cooled yesterday. We even have lava tubes that were so well insulated they trap ice inside year round, which is crazy to think about considering New Mexico is a hot desert. So why are they all clustered here? They're sitting in this transition zone. On the east you have the Colorado Plateau. Think of the Grand Canyon. It's thick, it's sturdy, it's a cold block of crust. On the west you have the Basin and Range. Think Nevada. It's thin and broken. And if you look at this image that I have on the right here, you can see all of those labeled. Colorado Plateau, Basin and Range, and you even got your Rocky Mountains on there as well. But we're mainly looking at the cracks between the Colorado Plateau and the Basin and Range extension. And what you notice is at the margins, at the boundaries of each of these contacts between Basin and Range and Colorado Plateau are where we get these volcanic fields. All of these volcanic fields are popping up right at the cracks between the two zones. And that's mainly known as these fractured zones because of faulting. And that's where magma is taking the path of least resistance, right? It's harder for magma to melt through all of the rock, but it's easier if there's cracks there to already be able to flow through, right? And that's basically where you get into faulting, and faulting creates cracks. I'm not going to go too in depth on that. Just notice that most of these volcanic fields are occurring at these fractured faulting boundaries. So let's get into the nitty gritty now, shall we? So let's talk about lithospheric foundering. So the stretching I was just talking about isn't really the whole story. To get the volume of lava that we see, we need something more dramatic. We need lithospheric foundering. So here's the concept. And I love to start with an analogy. Imagine you have a spoon and you dip it into cold, heavy honey or molasses and you hold it over a bowl. What happens? Gravity pulls the heavy liquid down, it forms a droplet, and eventually the droplet gets heavy, it detaches, and it falls because of gravity, right? So let's look at this diagram that I have here on the right. This is happening to Earth's lithosphere as well. Over millions of years, the bottom of the tectonic plate cools down. As rock cools, it gets dense. Sometimes it even changes into a super heavy rock called eclogite, and eventually this root becomes heavier than the hot mantle underneath of it. And so it becomes gravitationally unstable and it starts to drip. So looking at the image on the right, you can see that drip process occurring. That lithosphere is getting so heavy, heavier than the asthenosphere, can't really float anymore, so it's got to drip down. So when the heavy drip finally breaks off and it sinks into the abyss of the asthenosphere, two things happen immediately. You get the bounce, and this is when the crust above it, freed from the heavy anchor of that lithosphere, bobs up and creates mountains. I mean, think of it as a boat on the asthenosphere, right? It's just bobbing upwards because weight of the anchor of the drip is slowly dropping downwards. You've also got another concept called the rush, and this is when the hot asthenosphere rushes in to fill the hole or the gap that is left behind as the droplet is slowly sinking the lithosphere. It depressurizes and melts, and boom, you get a pulse of basalt volcanoes on the surface. A really interesting concept here. So you've got the pipe representing those basaltic explosions there as the asthenosphere is filling in the gap as the lithosphere, heavy lithosphere, is dropping, leaving those void gaps. And so where is this occurring, right? It's got to occur somewhere in order for us to study it. So let's look at the Sierra Nevada mountains. So we aren't just really guessing where this happens. We can see it in real time. And a good example of this is the Sierra Nevada in California. They've done seismic scans and found a massive blob of cold rock sinking deep into the mantle. And these are old roots of mountains. So we're looking in this IA to TR area there, two really cold blobs. And again, this is the Sierra Nevada mountains. And it's showing that this dripping process dripped off about 3.5 million years ago. And when it fell, the Sierra Nevada mountains shot up in elevation. And the Big Pine volcanic field nearly erupted in an instance. So it's kind of crazy to look at when you think of the real life example here in the Sierra Nevada mountains. I mean, they're huge area. And I'll actually go back to the image here just to show you that volcanic field. That Big Pine volcanic field is occurring in this location here. So again, you've got the Sierra Nevada mountains here. This is where that blue bulb was here. That cold root of ancient mountains. And that dripping sequence, as seen here, caused those mountains to bob on top of the asthenosphere, causing the mountains to rise, and the Big Pine volcanic fields to erupt as the asthenosphere was filling that in. Okay, now you need another version of supporting evidence, of course, and another case study here is the Colorado Plateau, as discussed earlier. So we can see it in Arizona too. On the edge of the Colorado Plateau, the mantle is flowing around that thick crust like water rushing around river rock, right? It's eroding the edge of the plate, knocking loose small chunks, and that's what's fueling the volcanoes that we discussed in those Arizona volcanic fields. It's active erosion 50 miles down. Crazy to think about. So it's kind of a contrast from the Basin and Range area in the Sierra Nevada mountains, a similar process, but it's as the mantle is flowing around and eroding the edge of these chunks of the Colorado Plateau, causing more foundering to occur, causing more dripping to occur, and a Lithospheric rushing in and causing the volcanism that we see in Arizona. So to wrap this up, again, these are my reference. I'll go over these later. The Southwest looks quiet, but it's actually really dynamic. It's a churning system. The crutch is stretching like taffy. The deep lithosphere is dripping like heavy honey, and the mantle is rushing up to fill the gaps, creating the landscapes that we love and see today. It's a reminder that Earth isn't finished building itself. It's still moving right under our feet. So that's the end of my project. Again, if you want to read some really cool papers on lithospheric foundering, please check out these references. They are awesome. They can teach you more about what I've covered today. And thank you guys so much for watching.